Predicting equilibrium concentrations. This is kind of gross, but they're making potato chips. So whether you're making potato chips or you're trying to grow some plants and adding some fertilizer or working with pharmaceuticals, it's very important to know the concentration of product at equilibrium, or even the concentration of reactant that is left, that didn't react at equilibrium. So being able to predict these concentrations of reactants and products at equilibrium is a really important skill and very, very applicable. So how do we know when we're at chemical equilibrium? We've seen this demonstration before, but let's just take a look at it again. So notice I'm not getting much at all as a reverse reaction. It's all going in the forward direction. When will I reach equilibrium? When the heights are the same? No. I'm going to reach equilibrium when I have the same amount in each beaker, going backwards and forwards. Because remember, equilibria is dynamic. So that means I have the same amount of product forming as I do reactant, right? Going in both directions. The amount of product and reactant, the concentration isn't changing over time. So we've heard that equilibria are dynamic. Well, when a chemical equilibrium is dynamic, that just means that reactants and products are always forming. You can't stop it. Well, if they're always forming, then how do you know when equilibrium is reached? Well, when the amount or the concentration of reactants and products is not changing over time. That's when equilibrium is reached. When the amounts or concentrations, same thing. So when the concentrations of reactants and products is not changing over time. Does not change over time. They're constant. Then you're at chemical equilibrium. Writing equilibrium constant expressions. How do you write equilibrium constant expressions? Well, you pretty much just write equilibrium constant and write all the concentration of all the products. And all the reactants in the denominator, all their concentrations. Now there's one last little thing. You raise them, these concentrations of reactants and products, you raise them to a power, and that power is always the stoichiometric coefficient. So whatever the stoichiometric coefficient is for that product or reactant in the chemical reaction, that becomes the power. What is never included in any equilibrium constant expression? So these reactants and products, you never ever see them in a Kc expression. What are they? Solids and liquids. It's strange. We never really thought of this before, but water, pure water, liquid water, has a concentration. In fact, it's 55.4 molar. So if you have pure water, a liquid, you don't write it in the Kc expression. It's a constant number. It's 55.4 molar. It doesn't matter how the amount, the concentration is always 55.4 molar. So pure liquids and pure solids we leave out. Okay. Those numbers actually are brought into the Kc number, and we'll see that. Let's do a little practice here. Write the equilibrium constant expression for each reaction. Okay. So for the first one, Kc, products over reactants. Concentrations raised to their stoichiometric powers, leave out solids and liquids. Do that for each one of these. So for the first one, you'd have brackets, concentration of calcium chloride, You can raise it to the 1 because that's a 1. But a lot of times we leave out the 1s, right? But in the denominator will be the reactants, chloride and the calcium ion. Raise them to their stoichiometric powers. Chloride is a 2, calcium's a 1. B. The equilibrium constant is products over reactants. The reactants are the same, calcium and chloride ion squared, but in the numerator, we just have a 1. Did you catch that? Because we have a solid. How about the bottom one? Kc, products over reactants. All we have for products are oxygen gas and CO2 gas. A lot of times we just leave out the gas symbol. The last one, products over reactants. Products, chloride squared, and bromine, you could say times 1, but you really don't need to. It's a pure liquid. Bromide concentration squared times the chlorine gas. Okay? Products over reactants raised to their stoichiometric powers. Using ice tables to predict reactant and product amounts at equilibrium. This is the method we're going to use to make these predictions of reactants and products and find out how much there are at equilibrium. So let's take a look at this question. We have 8 moles of A and 6 moles of B. They're initially present. And then at equilibrium, we have 6 moles of C. How many moles of A and B are also present? So they always give you a chemical equation. So we've got it. And then we make a table with 3 rows. Here's the top row, initial, little letter I. Second row, change, letter C. Equilibrium, letter E. There's where the ice is coming from. Ice table, initial change in equilibrium. The initial row is pretty easy. You just put in whatever numbers they told you. Copy them. 8 moles of A, so put in an 8. 6 moles of B, put in a 6. And they didn't say anything about C, so you put in a 0. I like to write dashes instead of zeros. It makes the tables look better. Change. Change is always minus x's for reactants, plus x's for products. But here you have to take the stoichiometric coefficient into account, because the change for A is twice that of B, because look at the stoichiometric coefficient. Okay. And remember, they're negative. These are reacting. These amounts of reactants are decreasing. So these changes have to be negative. X for product, but remember it's 3x. That stoichiometric coefficient has to come in front of that x. And you can put a little plus sign if you want. Okay? So it's always minus x for reactants, plus x for products. And don't forget the stoichiometric coefficients. The equilibrium row, just add up the initial plus the change. So you'd have 8 minus 2x, 6 minus x, and 3x plus 0 is just 3x. So that equilibrium row, this is our answers. There's our answers. We just have to find out what x is, and we will know the amounts of A, B, and C, and we'll be done. Okay. They told us at equilibrium 6 moles of C. So that means this has to be 6. Right? So 6 equals 3x. What equals x? 2. Right? So if x equals 2, that means that I have to have 4. 6 minus 2 is 4. 4 moles of B. 2 times 2 is 4. 8 minus 4 is, again, 4. So my answers would be 4 moles of A, 4 moles of B, and 6 moles of C at equilibrium. Okay. Let's try this again. What is the equilibrium composition? So they're asking for what are the amounts at equilibrium. That always means do ice. Make an ice table. Whether it's a mole table or a concentration table, make an ice table. Okay. Now they say, so we just as well start, set it up. So in the initial row, 4 moles of calcium, 6 moles of phosphate, and they said initially there's none of this calcium phosphate, dash. Okay, remember minus X for reactants, plus X for products for the change. So this is going to be minus 3X, minus 2X, and plus X. Add up the initial and change row to get the equilibrium answers. 4 minus 3X, 6 minus 2X, and X. Okay. They say at equilibrium we have 0.5 moles of calcium phosphate. So that means this has to be 0.5 moles. So you know what our X is. So 4 minus 1.5 is 2.5. We have 2.5 moles of calcium. Right? We'll have 6 minus 2x. So 6 minus 2x is what? 6 minus 0.5 times 2 is 1. 5 moles of phosphate. And then we'll have 0.5 moles. Forget about that, the calcium phosphate. .5, 5, and 0.5. What is the equilibrium composition? Oh, there it is again. So that means do ice. For the below reaction, if initially present were 1.5 moles of calcium, ion, 2.75 moles of hydroxide, none of this stuff. Okay, here's our equilibrium answer. So our change row, minus 2x, minus 3x, plus 2x. So 1.5 minus 2x would be my answer for calcium. 2.75 minus 3x will be my equilibrium moles for hydroxide. 2x will be my equilibrium moles for calcium hydroxide. But we know that's 0.25. Right? So my 2x has to be 0.25. So my x, 0.25 divided by 2 is about 0.125. Okay. So now I can find everything. At equilibrium, I'll have 1.5 minus 2 times 0.125. That'll be my moles of calcium. 1.5 minus 2 times 0.125, about 1.25 moles of calcium. I'll have 2.75 minus 3 times 0.125. 2.75 minus 3 times 0.125, about 2.375 moles of hydroxide. And they said that my calcium hydroxide was just 0.25. Forget about that. There's my answers. And realize that that calcium hydroxide is 0.25. Don't write 0.125 for it, because that's X. Calcium hydroxide is 2X, which is 0.25 moles. Okay, a 4-liter vessel containing 0.0148 moles of phosphorus trichloride, 0.87 moles of chlorine, and 0.0126 of phosphorus pentachloride at 230 degrees Celsius is in an equilibrium mixture. Calculate the value of Kc for the reaction. Okay. Is this an ice problem? Are they asking for the equilibrium composition? No. They are asking for a value for Kc. Okay. So Kc is what? Just start with what they're asking for. Kc is the concentration of products over reactants. Remember that? In brackets? Brackets, PCl5 divided by phosphorus trichloride and chlorine gas. Everything's raised to the 1 power because that's what the stoichiometric coefficients are. So we just need to know what these concentrations are, plug them in, and then we'll have our Kc. Do we know these equilibrium concentrations? Well, it contains these moles of things in an equilibrium mixture. So that means these moles are the equilibrium moles. We don't need to make an ice table because they told us the answers. They're just in the wrong units. We need concentration, not moles. Do you remember how to get concentration? Remember concentration? Big M, moles over liters. So divide the moles by the liters for each one, and we'll have our concentrations. So for PCl5, what's our moles and what's our liters? For phosphorus pentachloride, here's phosphorus pentachloride, 0.0126 of phosphorus pentachloride. 0.0126 moles divided by how many liters? 4. Everything's going to be 4 liters because that's the volume of the container. The denominator, phosphorus trichloride. Here's 0.0148 moles of phosphorus trichloride. 0.0148 moles over 4 liters. Need one more. We need the chlorine. Chlorine is 0.087. 0.087 moles over 4 liters. And we'll have our answer. Okay. You can do it in parts if you want. 0.0126 divided by 4, you get about 3.15 times 10 to the negative 3. 0.0148 divided by 4, you get about 3.7 times 10 to the negative 3. And 0.087 divided by 4, you get about 0.02175. Okay, so let's take 3.15 times 10 to the negative 3 divided by 3.7 times 10 to the negative 3 divided by 0.02175. I get about 39.1. Write the expression of the equilibrium constant for the following reaction. Write the expression. So remember, that just means Kc equals products over reactants, their concentrations, raised to their stoichiometric powers. And remember, leave out solids and liquids. So leave that one out. Leave that one out. What's left? We'll have products all over reactants, raised to their stoichiometric powers. It's kind of odd, but it's a half, so we have to write in a half. That's the stoichiometric coefficient. Nitrogen monoxide reacts with bromine to give nitrosyl bromide. A sample of 0.0524 moles of nitrous oxide, nitrogen monoxide, with 0.0262 moles of bromine gives an equilibrium mixture containing 0.0311 moles of NOBr. What's the composition of the equilibrium mixture? What is the composition of the equilibrium mixture? That means do ice, right? Whenever they want equilibrium amounts, it's always do ice. So set it up, see if you can get the answers. So hopefully your table will look something like that. Now they had to give us some information so we can figure out what X is. Equilibrium mixture contains 0.0311 NOBr. So this has to be 0.0311. So 2X is 0.0311. What's my X? .015. Okay, it depends on how many digits you want to carry there, but somewhere around 0.0156 would be my X. So using that number for X, just get your answers. 0.0524 minus 2 times 0.0156, 0.0212. 0.0212 moles of NO. So here's my equilibrium answers. And 0.0262 minus 0.0156, about 0.0106 moles of bromine. And then the NOBr we said was 0.0311. So there's my equilibrium answers. A 2.5 mole sample of phosphorus pentachloride dissociates at 160 in 1 atmosphere to give 0.338 moles of phosphorus trichloride. What is the composition of the final reaction mixture? So again, what's this composition? Do ice. So I have 2.5 moles of phosphorus pentachloride present initially. Okay, nothing else. The change rho minus X, X and X. Equilibrium rho, 2.5 minus X, X and X. So I get 0.338 moles of phosphorus trichloride at equilibrium. Okay, well that means this has to be 0.338 too then. So I can write my answers. At equilibrium, I'll have 0.338 moles of PCl3. I'll have 0.338 moles of chlorine, and 2.5 minus 0.338 is about 2.162 moles of phosphorus pentachloride. Okay, so these problems really aren't so bad. Just realize when they're asking for the composition, when they're asking for the amounts at equilibrium, that means do ice. If they're asking for a Kc, an equilibrium constant expression, that means write products over reactants, right? those brackets, raised to their stoichiometric powers. Okay, good luck.